Okay, so to postulate something is to suggest or assume the existence of a fact or a truth. This is not provable. That's the main point. So a postulate is a thing that's assumed to be true. It's the baseline reasoning. Have you ever thought about that? How do you know you exist? It's called a near infinite regress. You back up to say, how can I be sure of anything? Eventually you reach the starting assumptions. Have you ever heard of I think, therefore I am? Okay. Who said that? I've gone blank. Anybody? We'll look it up. What's that? Come on.
Was it like Plato or something?
No, but I'll pull it up and I'll email it out. But the point was he was trying to figure out how can I be sure of things, right? And so he was backing up, and finally he got to the point where he was doubting everything, and finally he said, wait a minute, if I'm doubting, then I at least exist, because there'd be no one to doubt. And so he says, I think, therefore I must exist. So you at least know you exist because you're doing the thinking. That would be an unprovable postulate. That would be the very beginning. At least I exist. Now, you can't prove that anybody else exists. Your brain may be the matrix, and we all exist inside of it. And it's creating all of the input and all of the relationships and everything around the natural world. And that's called solipsism. Okay. Again, you can't really prove solipsism is wrong. That you're the only brain and you've created all of this sensory input. Okay, so that ought to blow your mind. My point is that you have a starting set of assumptions, and these are the starting set of assumptions for physical chemistry, for quantum mechanics. Okay? And there's really a small set of them, because once you have some starting assumptions, then you can build upon that. And so we build upon these starting assumptions and how we interpret the pieces of quantum theory. So postulate number one, the state of a quantum mechanical system is completely specified by a wave function. So when we've talked about wave functions, when you ask what is a wave function, it doesn't tell you what it is. It just says that everything about the system is governed by that wave function. But what is the wave function? We don't answer that question. It just is a function that describes a particle or light or some quantum system, and all the properties of that particle can be defined by operating on that wave function. One of those properties is this probability that a particle can be found at a given time and in a spatial dimension is the square of the wave function. So really the wave function itself, the amplitude, we don't really have a claim as to what that means. But if you square it, then we're saying that's location. We're saying that the particle probability over space, how it's smeared across the x-axis in our example, when you square the wave function, then that intensity pattern tells you where the particle is. Okay. It's a postulate. We've set that up as a baseline assumption. Then we can go to the lab and we can verify that, and it does seem to hold, but we didn't learn that from someplace. We started with that. Okay. Now, wave functions have to have certain properties for them to work in a quantum mechanical system. It can't just be any function. It can't be tangent. It can't be 1 over x. Okay. 1 over x, when you go through 0, it goes to infinity, right? When x goes to 0, coming from the top, it goes to infinity. Coming from the bottom, it goes to negative infinity. So in the middle, it's not defined. At 0, 1 over x is not defined. And so it's not finite. And so it's not a good wave function. So there are certain functions that can't be wave functions. 1 over x is one of them. Also, you can't have a function that doubles back on itself. Like x squared equals y squared, you know, the equation for a circle. Okay, that would double back on itself. You give a particular x and you have 2 y values. Okay, so that can't be a wave function. Okay, so it's got to be single valued. It also can't be sharp. You see that b there? It's got a point right here. That function's continuous, meaning for every x value there's a single y value. but it's got a sharp kink in it. What's going to happen when you take the second derivative of that wave function? The first derivative, if you take the slope, and if I come at it from high values, I've got a slope here that's positive. You see that? But if I come at it from below, the slope is negative. So at that point, the slope is not defined. If I come at it from the high value, I got a positive slope. If I come at it from the low value, you've got a negative slope. One's above the axis, one's below the axis if you take the second derivative. And so the second derivative is not defined in that case. And since the Schrödinger equation is the second derivative, using the Hamiltonian, we've got to have a good second derivative. And so we can't have any kinks in our wave function. And then we also have to have continuous functions. We can't have something that's broken from the very beginning. So those are some restrictions on the types of functions that are valid wave functions. And if you have a valid wave function, you can use it to describe the particle properties that we're talking about. When we say that we have to square the wave function, and that is going to give us the probability distribution, what if we look everywhere for our particle? Like if we say that particle is in this room, and we have a wave function that defines its location in this room, and we square that wave function, if we integrate from the front of the room to the back of the room, from the left to the right, and from the bottom to the top, what should our probability of finding that particle be? It should be 1. And so all our wave functions must be normalized. So if you square that wave function and integrate over all space and you get 1.5, what are you going to have to do? You're going to have to put a constant in that wave function to reduce its value, so that when you square it and integrate over all space, the result is 1. We force them to be normalized with the normalization constant. And so that's normality. Wave functions need to be normalized. But they also, whenever we have quantum numbers in those wave functions, we have quantum state 1, quantum state 2, quantum state 3. We don't want quantum state 3 to just be the sum of 1 and 2. We want them to be linearly independent. And the word for that is orthogonal. Now in high school math or geometry, orthogonal meant 90 degrees, right? But what we really meant was that y is really not just the x-axis twisted a little bit. It's not related to the x-axis at all. In other words, I can pick a y value and I can pick any x value and it doesn't change that y value. So they're orthogonal. Now you can take that into infinite dimensions and you can say x, y, z, r, t, and so on. And well, just think in 4 dimensions. X, y, and z and t, time. Time is orthogonal to x, y, and z if the object is stationary. So I'm standing here and time is moving. So time is independent from my position. And so there's 4 dimensions that are orthogonal. And this is just saying that all of the different quantum states need to be orthogonal to each other. So when you take a wave function with quantum state 1 and a wave function with quantum state 2, 3, 4, 5, and you integrate over all space, so when n is not equal to n prime, you do integration of all space of those 2 wave functions multiplied by each other, you get 0. So that's what's being shown by this matrix here. Okay, this is the first 5 quantum states for a particle in a box multiplied by each other. And when wave function 1 is multiplied by wave function 1 and integrated over all space, I get 1. And when wave function 1 is multiplied by wave function 2 and integrated over all space, I get 0. And so this is just a sort of a nice 5 by 5 matrix showing orthonormality. Orthogonal when the numbers are different, and normal when the numbers are the same. Okay? And that's a property of normalized wave functions. And so this is shown in shorthand by this fellow's name, Kronecker delta. So this is all in one statement, that the integration over all space of a wave function with 2 quantum numbers, so quantum number n and quantum number n prime, the integration over all space is equal to this delta n prime n. And this is the definition of that Kronecker delta. It's equal to 1 when n prime equals n, and 0 when n prime is not equal to n. And then the result is just shown in that matrix. What does this mean for you? Just that you're going to normalize your wave functions. That's all it is. Okay. We're not going to suggest any wave functions that are not orthogonal in this class. But we're going over the baseline postulates for quantum mechanics, and this is one of them. Let's just show some integrals over all space for these different ones. That 5x5 matrix showed you the results, but these graphs, you may not understand what's going on in class today, but I would like for you to go into the notes and look at these until it clicks, okay? So what do we have here? We have wave function 1 times wave function 1, and so that's the blue times the purple. They're right on top of each other. And then we integrate over all space. So as we're going along, we're adding up the area under this curve. And you see it's getting bigger and bigger and bigger. And here it's still being added, but it's adding less and less till the end. And so the curve goes up. It's really steep here when you're adding a whole bunch. And then it starts to taper off. And then that final result is 1. Okay. So you integrate over all space from the left side of the box to the right side of the box. That's all space. And when you get to the end of the box, the integral is equal to 1. So that's all integration is the area under the curve. And so all of these, whether it's 2 times 2 or 3 times 3 or 4 times 4, when you integrate over all space, then you get 1 for a normalized wave function. Look at these. This is 1 times 2. And so in all of these curves, it's blue times pink equals red. So blue times pink equals red. Actually, it's the sum of blue times pink is equal to red. And so if you look at this area here, we have pink times blue. Notice pink is above the x-axis, so it's positive. And blue is above the x-axis, so it's positive. So we have some positive area under this curve. If you multiplied positive times positive, and so the integral goes up to a maximum value here. But look, pink went negative now. And so I have a negative number times a positive number, and so the result is going to be negative, and so it subtracts everything I gained. And by the time I get to the end of the box, I have 0 as my result. And so this is just proving to you what the integral is doing from left to right. The integral result is when you get to the end of the box, you've integrated over all space, and the result is 0. For 1 times 2, here's 1 times 3. So quantum state 1 is the blue one. Quantum state 3 is the pink one. It's got 2 nodes, okay? And the red is the integral. Here's 2 times 4. So the blue one is 2, it's got 1 node. The pink one is 4, it's got 3 nodes. Integrating the multiplication of those 2 functions, and I get 0. So it's just, again, showing you the integration over all space of those 2 functions times each other. Question? Okay. Postulate number 2, observables. For every observable or measurable quantity, there's an operator in quantum mechanics. Now, most of the time in math, our operators that you've been dealing with have just been like multiplication, divide, times, subtract. But in these cases, our list of operators has expanded some. First derivative, like d by dx, is an operator, or the second derivative is an operator. So an operator is something that acts on a function. And this is saying that an experiment in the laboratory has a corresponding operator that we could use to simulate that experiment. And so remember I said simulation is the key to understanding. If we can simulate a result, then we can understand it. And so the pioneers in quantum theory have come up with these operators that simulate the various measurable quantities that we have. So we can measure position, so there's a position operator. We can measure energy, and so there's an energy operator. That's the Hamiltonian. Okay. We can measure momentum, and so there's a momentum operator. In this class, all we're really going to deal with is the Hamiltonian, the energy operator. But we'll see the position and the momentum operator next. So here they are. This is a table of the different operators. And so that's the momentum operator. It actually has an imaginary, or it's a complex operator because it has an imaginary I there. It's the first derivative with respect to x. These are all written in one dimension in line with our course, doing things in one dimension. The kinetic energy is just that second derivative piece of the Hamiltonian. Position, the operator is just x, so it's the x-axis multiplied by the wave function. Potential energy is V of x. That is left generically because we don't know the system. You know, it could be a harmonic oscillator where you have a parabolic well. It could be our particle in a box where it's just set to 0. It could be the hydrogen atom where you have a Coulombic attraction of a negative charge and a positive charge. So it could be that Coulombic attraction function. That could be the potential energy. And so they put the potential energy together with the kinetic energy, and you have the total energy, and that's the Hamiltonian. And that's the one we're going to use the most. You're going to use that in lab, and we'll see it later on today. Yes?
Lab used a different Hamiltonian. It had h squared over 8m. Would you prefer the h bar?
Okay, this is the Planck's constant, and it's h bar. What happens with that is it's really just h over 2 pi. So that's a good question, or good thing to point out. And so in the lab, we had this, and it was h squared over 8 pi squared m, and the pi squared will be canceled out by some of the stuff that comes out of the wave function. Okay, so the pi's will go away. But yeah, that's where the 8 came from instead of the 2. So it was 2 squared inside of h bar squared, and it came out multiplied by the 2. So yeah, it's a good thing to point out. Postulate 3, eigenvalues. So whenever we take a measurement of an observed value, it will yield an eigenvalue of that operator. So these operators are eigenvalue equations. There's a little slide at the end of this set that talks about what that word means. It just means the proper value of that calculation. Whenever we do these problems, well, I'll just have to show you by example what an eigenvalue is. But it's mainly a vocabulary word for us. If I say the eigenvalues of the Hamiltonian, that's straight up CHEM vocabulary. If you don't know what the Hamiltonian is, you're not going to figure out what an eigenvalue is. Okay? What is the Hamiltonian? It was just on the previous slide. What does it give us? Energies. So focus on the word energies. The Hamiltonian gives you the energy levels. Okay? And so eigenvalues and energy levels mean the same thing. So when I say the eigenvalues of the Hamiltonian, I'm talking about the energies. But what if I said the eigenvalues of the momentum operator? Those would be the momentum values, yeah. Okay. So the eigenvalues of the position operator would be the positions. Expectation values. So if you took an experiment or a quantum system and you measured it, you know, you prepared the system many different times and you took a single measurement on each of those and you averaged those values, that average would be the expectation value. We can actually calculate that without doing the experiment by using integrals. Integrating those wave functions, we'll actually get the variability in those measurements, and we'll be able to predict not only the value but also its uncertainty. And that would be the expectation value. And so here's some examples of the energy eigenvalues using that expectation value mathematics. So I've got Dirac notation on the left, and I've got it written out in full form using integrals on the right, just to reinforce what we're meaning by Dirac notation. So look how short Dirac notation helps us out. I mean, it really shortens things. So let's look at this. We've got this over here on the left is Dirac notation, and this is quantum states, so n and n here. So those are the quantum states. This represents the wave function. So this piece right here is represented by this whole thing, the wave function, as a function of x and t, although we're gonna ignore the time dependence, but it's written out explicitly here. The Hamiltonian operator is in the middle, and then this wave function here is represented right here. Does anybody know what this little star means? This right here. That's an important piece. The convention for our use of these integrals, the left wave function is going to be the complex conjugate. Complex conjugate. So psi star, I'll just give you an example so you know what I'm talking about. So complex. If psi is equal to the e to the I m phi, and you'll see some of these on the homework, then psi star is equal to e to the minus I m phi. So wherever there's an I, you change the sign. Now, what if we have normalized wave functions? What is this piece down here on the bottom? That's the wave function times itself integrated over all space. What does that equal? I think I heard it. 1. Okay. So that denominator is just 1 if you have a normalized wave function, and in all cases we do. So really the expectation value is just that top piece. And that top piece is the Hamiltonian, so that's the energy. So this piece right here will give us the energy of the first quantum state. And then this next one gives us the energy of state 2, the third one, state 3, the fourth one, state 4. So those energy levels, 1, 2, 3, and 4, those are the eigenvalues, and these are the expectation values calculated using the Hamiltonian. It's kind of a sandwich. We have the Hamiltonian operating on that wave function, and then we sandwich it with the complex conjugate and integrate over all space, and we get those expectation values for the energies. Now, spectroscopy uses these expectation values, and if you take the difference between state 2 and state 1, now you're calculating a transition. We've calculated the energies, but we know that when light comes in, if it's absorbed, we've got an energy difference. And so state 2 minus state 1 gives us the location of the peak in a spectroscopic measurement. And so that little diagram on the right is a spectroscopic diagram. You see the arrow going up, that's indicating absorbance. And so it's going from state 1 to state 2. We get that by taking the difference between these two expectation values and getting delta E. So that would be the transition equation. Would be this taking the difference between all the different energy levels. And then time dependence, postulate 5. We won't use this one, but I went ahead and included it for completeness. And that is, there's sort of a time operator. So we can take that wave function with the time element, which is essentially e to the t, and we can look at the variation in time. Once again, it's complex, so it's going to introduce I, and then we're going to deal with the complex conjugates as well. So time dependence, we can predict small changes in time, not really long changes in time. So those are the quantum mechanical postulates. Let's take a quick Kahoot that reviews the messy mathematics from last time. Okay. So if you have your notes from last time with the messy mathematics stuff, you might want to turn to that just so you can look at it. Okay, now this one counts. So be sure you log in with your login ID, ABC123, whatever your initials are, so that I can track your participation. Whoa, sorry. How do I get back? What happened?
The fourth tab.
Oh yeah, because the music's still going.
On
Oh, okay, that's what happened. I didn't realize if I hit Control 1, it would go to the first tab. I was trying to change the screen capture. One more. Okay, did I miscount? Somebody?
No, I'm just taking a while to load.
Okay. While you're doing that, I'm going to flip something. Yay, we're there. Okay, we get in before somebody drops out. Oh, it's kind of small. Can you see that spectrum? Okay, so there's a shoulder on that one peak. So there's a peak, and then here's the picture. There's the big peak, and a shoulder, and a little peak. So really 3 is the good one. Now, those that chose the green, why did you choose green? Yeah, so underneath that peak, there's like 150 or something like that. But you wouldn't know that just unless you knew what was going on with the experiment. So good job if you got those. Again, I say this is for credit. It's participation credits. You don't get points off if you miss or anything. Yeah. Okay, so this equation applies to which axis of the spectrum? Horizontal or vertical? Wow, even split. Exactly, even split. So I need to reteach. So let's look at this. This is the equation for absorbance. And so absorbance is that y-axis, the vertical axis, and it's Boltzmann factor times that intensity integral times the Gaussian line shape. Okay, let's look at which piece of the intensity equation is temperature dependent. And so that intensity equation has the Boltzmann piece, the transition moment integral piece, and then the Gaussian line shape piece. Which one of those is temperature dependent? Oh, so I gave it away. Yeah, it's the Boltzmann piece. So whenever you hear Boltzmann distribution, think temperature dependent. That's the thermal population of energy levels. Boltzmann is thermal equilibrium. So that'll help you throughout the whole year, even in the spring semester, that Boltzmann distribution is thermal population. Okay, which of these will calculate the emission intensity? So one of them was squared, one of them's not, in terms of that x in the middle. Slight favor, okay, good job on the 17. That top one with x, that's emission. The bottom one, so the top one is emission, and it has a single x, and you can remember that by it's just one photon coming in. Either emission, absorption, one photon, emission is it drops down, spits out one photon. What is the bottom one? It's got two x's. Scattering, and scattering involves two photons. There's a photon coming in and a photon leaving. Okay? And if it's Rayleigh scattering, there's no change in the energy of that photon. If it's Raman scattering, there is a change. It can go up in energy or down in energy, but there's always two photons in scattering events and only one in absorption or emission. I think I just told you this about 5 minutes ago. So, Boltzmann distribution calculates what? The intensities of the excited states, the thermal population of energy level, emission probability, or absorption probability. I heard a lot of yay! All right, there's two troublemakers here. Which one of these is the Schrödinger equation? It's too tiny. Okay. Do your best. The top one, 2.8, it has the Hamiltonian in it. 2.9 has just two wave functions multiplied by each other, and 2.10 it has the Hamiltonian. Good, yeah, that was the Schrödinger equation. Okay, yeah, see this top one is the Schrödinger equation. It's also the expectation value equation. 7 of 8. Which axis in the spectrum uses the transition equation? The transition equation is the difference between two energy levels. How many are just saying, well, last time it was the vertical axis, so this time it has to be the horizontal axis? That's what I would do too if I didn't know. Okay, it's the horizontal axis. So in the spectrum, where is the peak, right? That peak is the difference in energy levels. And so, of course, if you can't see the equations, it makes it hard to answer. But this is the difference in energy equations. That's the transition equation. It tells you where the transitions are going to occur on the horizontal axis. And the last question, the 1D particle in a box wave functions depend upon temperature, true or false? It's talking just about the wave functions. Yay, good job. So yeah, there's no temperature in that equation at all. And so that's a real great way of understanding the math. When you dig down into the math, you can say, hey, this can't be temperature dependent because there's no temperature anywhere in the equation. So it doesn't depend. Now, its thermal population with the Boltzmann distribution is temperature dependent. Good job. So let's play around with the Schrödinger equation and etc. Let's annotate some of them. So this, again, these notes, if you were to look at these on your own and pull them up independently, I just have a little restatement of the quantum postulates, but it's stuff we just covered 20 minutes ago. Invalid wave functions. So let's talk about the different wave functions. There are several. That's the particle in a one-dimensional box wave function. We're using that one right now in lab. Then there's a particle in a two-dimensional box. So this is like a square drum head. and it has wave functions too. And you'll see some pictures of this in the text. And it's, look what they did. They just had two sine functions, one going in the x direction, one going in the y direction. So this one is n pi x over L1. This is n pi y over L2. And then the normalization constant, this was 2 over L to the 1/2 power. This is 2 over L to the 1/2. Basically, it's the two normalization constants multiplied by each other. But one is L1 and one is L2. And so that's a normalized wave function for a particle in a two-dimensional box.
In lab, for the one-dimensional box, it had n pi over 2 added to the equipment.
Yes. Okay, that's something that I've done to move the center of the wave function over so that zero's in the middle. Okay? And the reason I do that is because when you look at the symmetry of the function, if zero's in the middle, it's easy to see if it's even or odd. Okay? And that's unique to my class, is to have that phase shift in there. But it really helps when we move into symmetry. So we'll do symmetry next, and we'll be able to easily see even and odd functions. So that's why it's slightly different. But if you can walk your way through that wave function in lab, you could understand what that does for us. It just slides that wave function over. Then we have particle on a ring. So this is a particle orbiting another location with a fixed radius. And this one has an imaginary I in it. So this is pretty much our only complex wave function that we deal with. And notice the complex conjugate doesn't do anything to our real wave function. So we don't have to worry about the complex conjugate for a particle in a one-dimensional box. But a particle on a ring, we have to pay attention. And there's a couple of homework problems with that, with this particle in a ring wave function for you to do, just so that you understand it's a complex conjugate. If you don't change the sign on I, that problem is a lot harder. You change the sign on I, it ends up being e to the 0 d theta, integrating basically 1 times d theta. So it's pretty easy. And then the vibrational motion. So then we get to a harmonic oscillator, and things get pretty complicated. Look at this wave function. Okay. Oh, great build up. Okay, there we go. We've got this Hermite polynomial, so even the whole thing's not even shown here. And there's a table of those polynomials in the book. Then you got this normalization constant, which has got all kinds of crazy stuff in it. And then it's e to the minus x squared over 2 alpha squared. So it's a Gaussian wave function. E to the minus x squared is a Gaussian piece. And then it's got this Hermite polynomial in front of it, which gives it even an odd nature depending upon what energy level it's in. So those wave functions are plotted in the text. You can find them. Just mainly for your own curiosity. These are the particle in a one-dimensional box wave functions. These are the ones we're dealing with, and you'll be working with them in the lab. And so let's normalize this wave function. So this is one of the tasks that you'll do in the lab. We'll start with this wave function, and then we have and this is the phase shifted piece too. And so by definition of the Born interpretation, this integral of the wave function squared is equal to 1. And so we have that n value in there. We've multiplied the wave function times itself. So we have n here and n here. These are the normalization constants. So we pull those out front into the denominator. Okay, so now since the arguments inside the sign are the same, then we can make this sign squared. And so then we look at sine squared, and I don't want to integrate sine squared. I know how to do the integral of sine or the integral of cosine, but sine squared, I'd rather have to reduce that power. So this is called a power reduction substitution. So whenever you have sine squared or cosine squared, you want to get rid of that power. So you've got to go find a substitution that gets rid of the square. And this is 1 here. So sine squared is 1/2 times 1 minus cosine times 2. So there's a factor of 2 inside the integral, inside the argument here. And And so this is a trig substitution. Sine squared then becomes this piece right here.
What's a trig identity?
Yes, and so how do when you were taking calculus, you had to memorize these, okay? But you're done with calculus. Now you just go find the tables in the back of the book. And that's the real trick, is to try to find the right one, right? So you're looking for all the sine squared ones, and you're going to have lots of options. But when you see the one that just has a cosine in it, you're like, I can do that one because I know how to do an integral of a cosine. So that's how you know. Because I remember asking myself, how do I know which one to pick, right? And so if you know how to do the integral or the derivative of sine and cosine, then that'll guide you into which identity to pick, okay? And so let's go ahead and take this. This becomes two integrals because we have a simple piece here, and then we have a minus sign, and we have another piece here. So let's break this into two integrals. We have the integral of 1/2 dx, and we minus the integral of 1/2 cosine this stuff, okay? This one's easy. The 1/2 dx, the integral of dx is x, okay? So that gives us that. And it's evaluated at positive L/2, and then you subtract this evaluated at negative L/2. Straightforward, right? That's an easy integral. I got that. Okay. And then this one, the derivative of sine is cosine, and so the integral of cosine is sine. And we don't, there's no sign change on that. And then you have the integral of what's inside. Okay. So that comes out front as the reciprocal. And then that's your integral, and you evaluate it at L/2 and subtract this same thing at minus L/2. Now, where do the L/2's go? They go in for x, right? And so the L's are going to cancel with that L, and the 2's are going to cancel with that 2. And so it's going to be pretty clean when we get to the next step. And so here it is, all substituted in with no omissions. Now, what I've been doing in talking you through this is what I want you to do when I talk about annotated work. So in lab, when you're doing this, everything I've been saying to you, like pull the ends out front, write that out. We pull the ends out front, we have the next line. So I don't want you to just show a page of math. I want you to annotate it. Tell whoever's reading what you're doing. Okay? And even down at the bottom, we say we have the integral evaluated at L/2 and minus L/2. And so those go in for x, and then you show the next line. Just why do I want you to do that? It's good communication to someone else who's not familiar with it, because they look at this line and that line and they don't know what you did. And so you're telling them what you did. And it's also good communication because who's the most likely person to read that page? You. So when you're studying in the future, you're talking to yourself. You're talking to your future self saying, here's how I got from line 5 to line 6. And if you can't write it out, then you don't know what you're doing. Okay. So that's what I mean by annotation. Now let's look at this really quickly. We've got some things that can simplify. So this is gone here, and L is gone, and we have n pi, and we have this 2 is gone there, and we have n pi. Now, what are the n's? N's are quantum numbers, and they're integers. And what is the sign? Let's see, let's just draw a sign here. It goes through 0 a whole bunch of times, doesn't it? Where does it go through 0? Pi, 2 pi, 3 pi. Every time there's an integer unit of pi, sign is 0. That means this is 0. Oh, missed it. 0. 0. Okay? Same kind of thing. And so sometimes it gets real easy when you evaluate that integral. You look down at the bottom and you say, oh, this is integer things of sign. And everywhere it goes through an integer multiple of pi, it's 0. What if this was cosine? It'd be just as easy, but integer multiples of pi inside a cosine are either 1 or negative 1. And so you might have 1 times some fractions and things up front, and the other piece might be negative 1 times some fractions. and then those things are going to cancel and the total result will be 0. Or it may not be, it may be non-zero. But a lot of times when you get to the end, you have these trigonometric functions, but they're evaluated at a particular piece that gives you a 1, a -1, or a 0. And so they look much more difficult than they are. So just don't be intimidated. Just hammer your way through, get to this point and say, okay, now I need to think about it. And thinking about it is what I just did with that drawing. That's the evaluation piece. Because this is the answer, but now you have to interpret it. And you have to look at it and say, okay, all these signs become 0. And so it makes it easy. And so then we end up with over here, this piece, which is just, let's see, let's go. And so then we end up with 1 over n squared is L over 2. And so the result then is n equals the square root of 2 over L. So that is the normalization constant. Now, we're out of time, but the next one is the Schrödinger equation in just as much detail. So you can go through this one and see yourself how easy that is.